Hi, my name is Cleo Salispar, and this is my science research presentation on the effectiveness of the Beczak Sill in attenuating water energy in various weather conditions. Traditionally, armored shorelines, or hard structures, have been utilized to protect upland property. These are man-made structures made of materials such as concrete or non-native rock, including bulkheads, break walls, and riprap. And these are very effective in doing their job in protecting upland property, except the problem with them is that instead of absorbing water energy like a natural shoreline would, it deflects water energy, causing offshore erosion and reducing biodiversity, making them not a sustainable method for protecting upland properties. As a result, scientists have developed living shorelines which serve as a less disruptive method for protecting upland property by utilizing native species to actually attenuate that water energy, to decrease it, and this can sustain biodiversity or even enhance it. However, in places where there's higher water energy, living shorelines don't serve as an effective method on their own, so scientists also developed hybrid living shorelines, which utilize both the hard method structure and the living shoreline as kind of a combination, and this method is effective in protecting upland property when water energy is a bit higher. An example of this would be a reef ball, a marsh bed, oyster reefs, sills, which is what I'm looking at, and native riprap, which, as opposed to traditional hard riprap, is made out of native rock and native plants. Salt marshes are a very common use of a living shoreline. Salt marshes attenuate wave energy and trap sediments to protect upland properties. However, the problem with them is that over time they decrease in effectiveness because they start to erode. And that's why including a sill around the salt marsh can be effective over time in keeping up that attenuation of water energy, making that a hybrid shoreline. There's a direct relationship between wave energy and erosion rate, and factors that contribute to wave energy include current speeds, wave height, current direction, and when there's a higher wave energy, there's a faster erosion rate. Overall, more research is needed because it gives guidance on future stabilization projects, and research developers and project developers can utilize more data, supplemental data, to prove that living shorelines and hybrid shorelines are effective in protecting upland properties. In order to develop my methods and materials, what I used was the Hudson River Sustainable Shorelines Rapid Assessment Protocol. And what this is it's a step-by-step outline of how to survey living shorelines along the Hudson River. It establishes a universal terminology, which creates a universal understanding of each report of each living shoreline along the Hudson River, regardless of who's collecting the data and regardless of location. And the most relevant topics within this manual for my project were stone count, crest measurements, erosion measurements, asset displacement, and most importantly, bulk energy measurements. I've really been in the driver's seat with this project, and my role is that starting sophomore year, I had to research this topic extensively. I developed my methods and materials and developed a test matrix going into junior year. This year, my main focus is collecting data and putting that into spreadsheets, and eventually my role will be writing the research paper and analyzing the data I've collected. My mentors have been there guiding me along the way. They helped me to develop my research question. They taught me the Hudson River Protocol, and they gave me and still give me assistance whenever I need it. My research question is, how does energy change in different weather conditions, and how effective is the Beczak sill in attenuating that water energy in different weather conditions throughout a calendar year? And it's a novel research question because there's no current data on how effective the Beczak sill is at doing its job in attenuating the water energy, and the Beczak sill is my study location. And there's no major research on how various weather conditions affect a single sill, and this is mostly because in the scheme of things, living shorelines are a fairly new development. My study site is the Sarah Lawrence College Center for the Irvine River at Beczak. It's in Yonkers, New York, right along the Hudson River in the Hudson River Valley. It has a salt marsh surrounded by a sill, making it a hybrid shoreline, and it's a research center which researches biodiversity in the Hudson River. So the reason they implemented a hybrid shoreline at this location was because it would sustain biodiversity as opposed to a hard structure. So in order for me to be able to collect data in the Hudson River, I need to go out in between peak low tides, and this is because that's when it's safest for me to enter the river to deploy my plaster casts. And these low tides are approximately 25 to 24 and a half hours apart, which is the time that my data collection occurs in. And what I do is I check the tide charts each week and I see when it would be optimal for me to go deploy the casts. In order to track weather conditions, I use the Stevens Institute of Technology tracking systems, which I put the data I find on this site into a spreadsheet. And this tracks things like surface currents, current direction, surface salinity, and more. And in addition to this, I also use weather apps to track humidity percentage, to track temperature, and to track water temperature. So the way I'm figuring out this difference in water energy on either side of the sill is I'm building casts of plaster of Paris, and the more they erode, the more water energy there is in the river. And these casts are built from plaster of Paris. They're approximately 225 grams each, and I put 4 of these casts on one rope, each 1 foot apart from each other. And in between these 4 casts, I put a pool noodle for flotation to keep them on top of the water. So in total, that means there's 16 casts deployed for each data collection. In order to keep these casts apart and afloat, I put them between poles, which I deploy 5 feet apart. So in total, there's 8 poles, and I deploy the casts and the poles in 4 locations around the sill. Location 1 being the outside southern end of the sill, location 2 the inside southern end of the sill, location 3 the outside northern end of the sill, and location 4 the inside northern end of the sill. The goal in my research question is to capture a variety of different weather conditions, and ones I really want to capture are a spring tide, which is where there's the biggest difference in tides within a month, a neap tide, which is where there's the smallest difference in tides within a month, a strong southern and northern wind, a storm event, a day where there's heavy boat action, a snow event, high and low temperatures, and high and low wind waves. Now, in addition to these bulk energy measurements, I'm also looking at changes within the sill itself, and changes within the sill itself can help to explain sudden trends of data. If they're not related to weather conditions, they could possibly be explained due to a change in the sill. And what I'm doing is a stone count measurement, which is where I'm tracking the movement of rocks on the sill. I place 5 16 by 16 inch squares on the sill, and I count the amount of large stones and small stones. In addition, I do crest measurement, and this finds differences in height on the sill, and both of these combined kind of give an idea of how the sill is changing. And then lastly, I capture wind wave height on both the southern end and northern end of the sill, which is used in my data in my weather spreadsheet and helps to capture the weather conditions on that specific day. This project has not been easy, as I've had to develop the methods and the materials of this project, and one of the challenges I ran into was keeping the casts afloat on the top of the water. Through trial and error, I eventually found that the most effective method was to put pool noodles between the casts to keep them on top of the water. And my hardest challenge was deploying the casts on the outside of the sill. Something I didn't expect to run into going into the project was that the bottom of the river on the outside of the sill is very rocky, so I couldn't simply hammer the poles into the ground like I could on the inside of the sill. So what I had to do was kind of experiment, and I figured out that putting a limestone brick filled with concrete and then putting the pole in that concrete would keep the poles up for a 24-hour period on the outside of the sill. And so I take those in and out of the river every time I go and collect data. And then lastly, freezing temperatures made it hard kickstarting this year to go collect data. At the end of January and all throughout February, I was unable to collect data because the sill was frozen over, and the immediate shoreline was also frozen over, making it so I couldn't access the inside of the sill or the outside of the sill. This is how I organize my results. This is for stone count. So what I do for stone count is I keep track of the date of the survey, the GPS location of the survey, the location on the sill in which I'm looking at. And again, I'm tracking 5 locations, and then I see how many large stones are within that 16 by 16 square and how many small stones are within that 16 by 16 square. And I do this every time I go out and collect data. This is how I keep track of my weather conditions. I aim to capture the weather conditions on a specific day because, again, that relates to the water energy. I capture the date of the survey, the special condition relating to the weather conditions I'm trying to capture, wind speed, wind direction, water temperature, wind wave height on the southern end and the northern end of the sill, current direction, surface current speed, surface salinity, peak low tides and high tides, outside temperature, and percent humidity. On its own, these results don't mean anything, but when compared to the amount of erosion, that's when they become significant. And these are my energy results with the plaster spheres. Again, I'm casting 16 spheres in groups of 4 with 4 casts in each group. I find the original weight, the final weight, the difference in weight, and then the average weight for each of these 4 groups. On this specific day, on January 15th, 2022, in group 1 on the outside southern end of the sill, the spheres eroded 31.75 grams, while on the inside southern end of the sill, they only eroded 14.25 grams, meaning that on that specific day, in those specific weather conditions, the sill on the southern end was over 50% effective in attenuating water energy, while on the northern outside end of the sill, the spheres eroded 37 grams, and on the inside northern end of the sill, they only eroded 7.5 grams, meaning that on that specific day, in those specific weather conditions, the northern end of the sill was very, very effective in attenuating water energy. So because my research question pertains to a full calendar year, all my data is comparative, meaning that I can't create data charts or tables until I have more data collected in a variety of different conditions. My independent variable in this experiment is the changes in weather conditions and changes within the sill. My dependent variable is the difference in water energy, and my constant is my data collection methods. My future focus and goals is I want to have 15 data points collected by October. I want to share my results with my mentors and communicate with them every 3 to 4 weeks or when needed. And I want to draft the introduction/methods part of my paper before the end of summer and hopefully have my research paper completed by the end of October. So why should you care about my project? Why are living shorelines so significant? Well, with the problem of climate change, there have been rising sea levels, which change current direction, which change current speeds, which changes wind speeds, all of which contribute to higher water energy. And this higher water energy increases the need for stabilization projects. And in urban areas such as Manhattan, New York, sometimes hard shorelines need to be implemented because there's an immediate need to protect immediate upland property. However, in residential areas, when there's lower water energy, there's really no need to implement hard shorelines, and living shorelines or hybrid shorelines can do just as an effective as a job. And there's even economic benefits to implementing living shorelines. For example, in a residential area, if you were to implement a hard shoreline, like I said, it would erode the offshore intertidal beaches, depleting your property value. And in addition, aesthetically, living shorelines are a lot more pleasing than a hard structure, making your property value go up. And it's also just very sustainable for the environment. It increases biodiversity. And yeah, I would like to thank my mentors for their amazing guidance, my family and my science research teacher for her consistent support, and the Tri-County Committee and judges for this great opportunity. Once again, my name is Cleo Salas-Barr, and this is my science research presentation on the effectiveness of the Beczak sill in attenuating water energy in various weather conditions.